13.6, the binomial theorem and probability. Managers at the Eco Landscaping Company know that a mahogany tree they plant has a survival rate of about 90% if cared for properly. If they plant 5 trees, what is the probability that at least 2 trees die? So, probability that at least 2 trees die is going to be the probability that 2 trees die plus the probability that 3 trees die plus the probability that 4 trees die plus the probability that 5 trees die, which is a lot of probabilities. To start with, an easier way to write this would be 1 minus the probability that 0 trees die or 1 tree dies, right? Because here we only have to calculate 2 probabilities. Here we have to calculate 4 of them. I'd rather do the option that's half as much work. So, at least 2 trees die is 1 minus the probability that 0 or 1 trees die. So, let's find the probability that no trees die, right? Survival rate of about 90% means the probability that any given tree dies is 10% or 1/10. So, the probability that no trees die, right? There's a 90% chance that it doesn't die, any given tree. So, 90% chance for the first tree, and then a 90% chance for the second tree, and then a 90% chance for the third tree, and then a 90% chance for the fourth tree, and then a 90% chance for the fifth tree. So the probability that none of the trees die is 0.9 to the 5th power, which is 0.59 approximately. Okay? Now, what's the probability that exactly 1 tree dies? So, exactly 1 tree dies, and 4 others don't die. You have a 0.1 probability that the first tree dies, and then a 0.9 probability for each of the other 4 trees. Okay? But this gives you the probability that the first tree dies and the other 4 don't. What about the probability that the second tree is the 1 tree that dies? So the first tree survives, and then the second one dies, and then the third and the fourth and the fifth survive. Okay, so you'll notice that turns out to be the same probability because multiplication is commutative. So it's just as equally likely that the second tree dies and the other 4 live than that the first tree dies. And we could do the same thing with the third tree, right? The first 2 live and the third one dies, and then the fourth and the fifth live. And so again, you get 0.9 to the 4th times 0.1. And hopefully you can see you could also do this for the 5th tree, the 4th tree, and the 5th tree. So what happens is you end up with 5 times 0.1 times 0.9 to the 4th. Right? 1 tree dies, 4 trees live, 5 ways that could happen. The first tree, the second tree, the third tree, the fourth tree, or the 5th tree being the only one that dies. And so what you get is it's about 0.33. So the probability that 0 or 1 tree dies is 0.59 plus 0.33, which is 0.92. 0.92. So the probability that at least 2 trees die, 2 or more, is 1 minus probability of 0 or 1, which is 1 minus 0.92, which is about 0.08, or 8% probability that at least 2 trees die. So this gets us the binomial theorem. If you're looking in your textbook wants to do this a different way, but the binomial theorem is better. So you get this formula. The probability of exactly k successes out of n, each with probability p, is k choose n, or combination of n choose k, times p to the k, times 1 minus p to the n minus k. So this part here, right, this is your combination. How many groups of k can we take from n, right? In the example we just did, that's how many ways can we pick one tree to die out of the 5. And so when we did that, it was 5 ways, right? We could pick each of the 5 different trees. What if it was pick 2 out of the 5? You could have the first and the second, or the first and the third, or the first and the fifth, or first and fourth, or the second and the third, or the second and the fourth, and so on, right? And that's where you get the combination factorial, n factorial over k factorial, n minus k factorial. So you use the combination because you're picking how many groups of k can you take from n. How many ways can we pick the 1 tree that dies, or the 2 trees that die, etc. And then you have this p to the k is the probability of success to the power that is the number of successes, right? If our success is a tree dying, then p would be 0.1, and our number of successes, k, would be 0 and 1, the way that we did it. And then we have this 1 minus p to the n minus k. This is the probability of failure, right? 1 minus p is the probability of failure. And then n minus k is the number of failures. If k is the number of successes, then n minus k is the number of failures. So the probability of success to the power of the number of successes times the probability of failure to the power of the number of failures, right? Because we have 2 successes, we have to have 3 failures if we've got 5, say. So the probability of failure to the power of number of failures times the combination of ways that we can pick 2 successes and 3 failures, or 1 success and 4 failures, etc. So problems that can be solved using this method are called binomial experiments. A binomial experiment exists if and only if these conditions occur. There are 4 conditions to be able to use the binomial formula. Each trial has exactly 2 outcomes, or outcomes that can be reduced to 2 outcomes. So the tree lives or the tree dies, 2 outcomes. Or we roll a 4 on a die, or we don't roll a 4. Or a child is a boy or a girl, or something. Outcomes, only 2 outcomes, or outcomes that can be something happens or that thing doesn't happen. And so for this one, we say that the condition is that each trial has to be binary. Binary. The outcomes of each trial must be independent. There must be a fixed number of trials. So you can't say, I'm going to flip this coin until I get a heads. That's not a fixed number of trials. I could say, how many heads will I get or what's the probability of getting 3 heads if I flip this coin 5 times? But I can't say I'm going to flip the coin until I get a heads, because that's not a fixed number of trials. And then the probabilities in each trial are the same. The probability of getting heads is always 1/2. You cannot use a binomial for things like pulling cards out of a deck, because then the probability is not the same. Also, those are not independent. So, if I write these conditions like this, this gives us the mnemonic that we use in AP Stats, BINS, B-I-N-S, for the conditions of a binomial experiment. Binary, independent, fixed number of trials, and the same probability of success. It's a little bit awkward. We took some liberties with the initials there, but BINS. Binary, independent, same number of trials, and fixed number of trials, and same probability of success. 8 out of every 10 persons who contract a certain viral infection can recover. If a group of 7 people become infected, what's the probability that exactly 3 people will recover? So our probability, P, of recovery is 8 out of 10, which is 0.8. A group of 7 people become infected, so our N, which is our total, is 7. And we want the probability that exactly 3 people will recover, so our K is 3. So probability of exactly 3 people recover, we're going to use that binomial formula. And so that's going to be the combination of 7 choose 3. How many different ways can we pick the 3 people to recover from the infection? Times the probability of recovery, which is 0.8, to the power of the number of people who recover, so 0.8 to the third. But if we want exactly 3 people, we also have to multiply that by the probability of not recovering, which is 1 minus 0.8, to the number of people who don't recover, which is 7 minus 4. Right? So C, the combination 7 choose 3 is the number of ways to pick 3 people who recover out of 7. Multiply that times the probability of recovery to the power of the number of people who recover. And then this here is the probability of not recovering to the power of the number of people who don't recover. And that'll get us exactly 3 people who recover and 4 who don't. So combination of 7 choose 3. We know our combination formula is 7 factorial over 4 factorial, 3 factorial. We're going to multiply that by 0.8 to the third for 3 people who recover. And then we're going to multiply that by 0.2 to the fourth for the 4 people who don't. And so 7 choose 3 is 35 times 0.8, not 0.08, times 0.8 to the third times 0.2 to the fourth. And then this is where your calculator comes in handy. Times 35. And this gets us a very small probability. It's about 0.03. So, very small probability that exactly 3 people recover, because there's an 80% recovery rate. If you do this probability for 5 or 6 or 7 people, you're going to get a much bigger probability. Managers at the Eco Landscaping Company know that a mahogany tree they plant has a survival rate of about 70% if cared for properly. We just did this. If 10 trees are planted in the last phase of a landscaping project, what is the probability that 7 of the trees will survive? The probability that 7 trees survive, our probability of survival is 90%. Our total N is 10, and our K is 7. So our probability that exactly 7 trees survive is going to be 10, well, it's going to be combination 10 choose 7, right? All the different groups of 7 trees out of 10. And then each of those groups has a 0.9 to the 7th times a 0.1 to the third probability, right? 0.9 to the 7th power, 7 trees that survive, 0.1 to the third power, 3 trees that die. And so 10 factorial over 3 factorial, 7 factorial, times 0.9 to the 7th times 0.1 to the third. And so we get, that's 120 times 0.9 to the 7th times 0.1 to the third. Point 9 to the 7th times 0.1 to the third times 120 gives us about 0.6 chance. 0.06 probability, about 6%. Again, if you did it for 7 or 8 or 9, or if you did for 8 or 9 or 10 trees, you would get a much higher probability as we get close to 90%. And that's it. I hope you enjoyed this probability lesson. And that's all that we're doing on it.